All right, let's get started. Good afternoon, everybody. Welcome to SIREN. My name is Sonja Schmid. I'm a faculty member in the Department of Science, Technology, and Society at Virginia Tech, and I also co-direct the graduate program in the National Capital Region in Science and Technology Studies. This is the 22nd event in a series of seminars, talks, and conversations on nuclear emergency response. It is part of my NSF Career Award on globalizing nuclear emergency response. And in the spirit of this type of grant, we emphasize the importance of both research and education in the area of nuclear emergency preparedness and response. And so all our SIREN speakers are meeting with graduate students as part of their engagement, and we plan to provide access to a recording of their lectures. SIREN, the Seminar on Interdisciplinary Research and Education in Nuclear Emergency Response, is generously supported by Virginia Tech's Office of the Vice President for the National Capital Region and the Policy Strategic Growth Area. Many thanks to the staff of the Virginia Tech Research Center's Executive Briefing Center and the I-Team for their support, and to the students, staff, and faculty in the Department of STS for helping to make this happen. Today's talk will be live streamed, and we have a new record of 130 remote participants signed up as of this morning. These attendees are joining us not only from our main campus in Blacksburg, other U.S. universities, federal agencies, and national labs, but also from abroad, including Canada, Britain, and France. Welcome to SIREN. If you are watching us online and would like to submit a question to our speaker, please send an email indicating your name and affiliation to siren@vt.edu. Also, if you'd like to be added to our mailing list, we use it only to announce SIREN events. You can now join our Google group SIREN series. Our next event will take place on March 22nd. We'll have a team from DOE's Office of Consequence Management address training for nuclear emergency response. Please stay tuned and help us spread the word. And now it's my great honor to introduce our speaker today. Dr. John Kelly is currently the Vice President and the incoming President of the American Nuclear Society. He recently retired from the U.S. Department of Energy, where he was the Chief Technology Officer in the Office of Nuclear Energy. He was responsible for establishing the strategic technical direction for the Office of Nuclear Energy's research, development, demonstration, and deployment portfolios. Prior to assuming the duties of Chief Technology Officer, he was the Deputy Assistant Secretary for Nuclear Reactor Technologies. His office was responsible for the civilian nuclear reactor research and development portfolio, which included programs on small modular reactors, light water reactors, and Generation 4 reactors. His office was also responsible for the design, development, and production of radioisotope power systems, principally for NASA missions. In the international arena, Dr. Kelly has previously chaired the Generation 4 International Forum and the International Atomic Energy Agency's Standing Advisory Group on Nuclear Energy. And prior to joining DOE in 2010, Dr. Kelly spent 30 years at Sandia National Laboratories, where he was engaged in a broad spectrum of research programs in nuclear reactor safety, advanced nuclear energy technology, and national security. In the reactor safety field, he led efforts to establish the scientific basis for assessing the risks of nuclear power plant operation, and specifically those risks associated with potential severe accident scenarios. His research focused on core melt progression phenomena, which led to an improved understanding of the 3 Mile Island accident and, more recently, the Fukushima Daiichi accident. In the advanced nuclear energy technology field, he led efforts to develop advanced concepts for space nuclear power, Generation 4 reactors, and proliferation-resistant and safe fuel cycles. These research activities explored new technologies aimed at improving the safety and affordability of nuclear power. And in the national security field, he led national efforts to evaluate the safety and technical viability of tritium production technologies. Dr. Kelly received his BS degree in nuclear engineering from the University of Michigan and his PhD in nuclear engineering from MIT. I met him at a small workshop on nuclear nonproliferation organized by students at William and Mary Law School last year, and I'm really thrilled that he agreed to talk to us today. Please join me in welcoming John Kelly.
Well, thank you, Sonja. This looks like it's working good. Appreciate the turnout, and hello to everybody watching on the video. Yes, we met, it was just about a year ago, I think, in William & Mary, where there was, the law school was having a session on nuclear law, not nuclear law, but environmental aspects of nuclear technology, and brought in a number of experts from principally the Washington, D.C., Virginia area to speak to them. So it was a very interesting and kind of a different audience at that time. Just a little bit about myself and how I kind of connect to this topic. I was in graduate school when 3 Mile Island happened, and up in Massachusetts there was quite a bit of sensationalist press on this topic. Clamshell Alliance was one of the dominant groups that were trying to stop the Seabrook nuclear power plant. Anyway, that event ended up being kind of seminal in my career, because after that event there was a ramp up of the NRC's Severe Accident Research Program, and I graduated just in time to be hired by Sandia, which was one of the laboratories that was doing significant work for the NRC in core melt progression, hydrogen explosions, steam explosions, the whole gamut of severe accident phenomena. So I got to see kind of firsthand not only the experimental work, but also the analytic work that then we then use in risk assessment and other types of studies. Spent about 20 years doing severe accident research, and then a few other things at the lab before joining DOE, and within about 4 or 5 months of joining DOE, Fukushima happened. Fortunately, I had maybe the right place at the right time, and so Secretary Chu quickly found me, and I was briefing him twice a day on what was going on at Fukushima. So it was quite an experience, and very, very, very exciting time in sort of a different type of way. But I think because of that, I have some firsthand experience about why it's so important to have effective and rapid response. Because when an accident like this happens, there's a lot of public safety decisions that have to be made, and these require prompt actions, and they need to be really focused. They have been really focused on being informed by estimates of the potential radioactive source term and its consequences. So if the accidents happen, then you have to worry about, do you evacuate or not? How far do you evacuate? These type of things. It's a very complicated task, lots of uncertainties. And in order to be effective, the capabilities to do this type of analysis need to be in place prior to the accident. And it's not just analytic capabilities, it's the physical assets that we need as well. The capabilities need to be accurate, timely, and credible. Accurate means that if you use extremely bounding type of estimates, you're going to get results that are probably not the best for public health and safety. And so you have to try to get as accurate as you can. And the time urgency requires that these capabilities can be assembled rapidly and deployed. So I just wanted to use this talk to kind of reflect on how emergency response has evolved over the last several decades. I'm going to focus on the 3 major power reactor accidents, TMI, Chernobyl, and Fukushima. But I just point out that there were some other accidents as well. SL1, Santa Susana, Fermi 1 Windscale. But they did not have the same kind of level of response that we saw from the other 3 power plant accidents. So let's just first reflect on what happened at TMI. Well, in terms of where we were, it was a general lack of knowledge of phenomena. As I said, the research program into that area had just sort of begun, and so it was very limited, the amount of knowledge. That led to a considerable amount of confusion and misinformation coming out. And in general, there was a denial of core melting from both the industry and the NRC. This later turned to be incorrect. And the press was generating sensationalist headlines, and I'll show an example. I've actually found a newsletter that comes from that time. I will point out, though, that the reactor safety study, WASH 1400, had been released in 1975, and this was meant to be a probabilistic risk assessment study. It was the first one. It had severe accident modeling, but it was very crude. and it identified that small breaks were important to risk, and TMI ended up being a small break loss of coolant accident. And so, this basically pointed to the fact that we needed to be very careful in our risk assessment, that we look at the broad spectrum of potential accidents. Now, the day after the accident, the NRC chairman, Joe Hendry, testified, and, again, based on the information they had today and their understanding, he said there was nowhere near a core meltdown. Of course, 5 years later, when they began to do the disassembly, they found out that they had a partial core meltdown. Significant damage, over half of the core had probably been damaged and melted, and there was a significant amount of molten material that was now frozen in the lower head. So, this, I think, really pointed to the fact that without good scientific and engineering information, it's very difficult to make sound decisions. And this is the one of the newsletters that I somehow kept over the years. It came out a week after the accident. It talks about the nuclear accident being over and how it stabilized. And then it says death toll mounts. Well, I think we all know today that there was no deaths from radiation. But it was using, the fact that there was some radiation and that there's no safe limit. And so it was talking about, what the potential could be years and years into the future. In terms of the local response, the governor advised the evacuation of pregnant women and preschool children within 5 miles. This was just within a day and a half, I think, of the accident. This was later increased to 20 miles. And some 140,000 people left the area, but more than half of the population remained behind. So there was some, concern, but I think, again, there wasn't really good information on what the real impacts of the accident were. So what happened after 3 Mile Island? Well, there's certainly a lot of lesson learned reports that were written. We had more regulations. I think a good thing that happened was this organization named IMPO was formed to basically self-police the nuclear power plant and really improve the safety and performance of all the nuclear plants. As I mentioned before, NRC's Severe Accident Research Program came into play in a big time, and there was significant resources spent to try to understand phenomena experimentally and then to build the analytical models. And there was this push for new designs that emphasize passive safety. And so today we see AP1000, ESPWR, which are reflecting the lessons learned from 3 Mile Island. Now let me turn to Chernobyl. So in this case, they had an accident that happened very, very rapidly, led to damage of the core, and then the graphite that was used as a moderator caught fire. And this led to massive amounts of radioactive materials being released to the environment. The emergency crews immediately started to use helicopters to drop sand and boron. This was to put the fire out and to prevent recriticality of the reactor debris. And I think they quickly realized that this was not going to be a long-term solution, so they began to build this sarcophagus within a few weeks. And just recently, I think last summer, there was an upgrade to that facility, which has been done in conjunction with the Western nations to give a more permanent stabilization to the site. And the officials closed the area off within 18 miles of the plant. Now, what was really surprising here was how long it took to evacuate. It was a day and a half before the people in the local town were ordered to evacuate. Day and a half. Well, most of the radioactivity had already been released by that point. The residents were told they would only be gone for several days, so they left everything behind, and of course they never actually returned. And this was the end of April, and May Day was a big day of celebration, and the Soviet officials made the decision not to cancel the May Day parade, and so outdoor parades were held in the region 4 days later. So it was, I think Sonia knows some of the reasons why that was, but it certainly is quite different than I think what we would expect to see today in terms of emergency response. In the U.S., I think there was both the NRC and industry cited differences in design, safety systems, containment as reasons that why a Chernobyl-type accident could not occur in the U.S., so it was largely discounted. However, there was impact on the production reactor facilities that DOE had. And in particular, there was a hard look at the safety issues of the defense production facilities, the reactors at Savannah River and Hanford to make tritium and plutonium. They both had very unique configurations, and as they dug into it, they realized that there was some vulnerability, so the K reactor power level was immediately reduced in half, so that it wouldn't have any kind of, it would reduce the probability of a severe accident. But eventually those reactors were shut down. Now, I wouldn't say they were shut down because of Chernobyl, but I think after Chernobyl, there was a view that these reactor designs needed to be redone, or maybe a new reactor built that would encompass better levels of safety and to basically avoid the kind of accident at Chernobyl and to mitigate consequences thereof. Okay, now let me turn to Fukushima Daiichi accident. This is one where I had more, as I said, personal view of, and can maybe go into some details of my observations from what happened during the emergency response. A couple of important reasons why the U.S. government was interested in the accident. Well, first, the reactors were of U.S. origin, they're General Electric design. What this means is that there were sister plants in the U.S. that were similar, or if not the same, model. And so what was going on there could potentially have an impact on the BWR fleet in the U.S. In some sense, we were fortunate that the NRC had conducted an extensive research program over the last, since TMI. And this meant that we had a wealth of information about severe accident phenomena, so that when the accident began to evolve, we had a better idea of what was actually happening. Additionally, a sister plant, Peach Bottom, which is in Pennsylvania, had been extensively studied in various risk studies, New Reg 1150, where, in fact, the station blackout scenario that Fukushima exhibited had actually been one of the cases studied in those risk studies. And so we had actually already had computer runs that would have simulated the progression of the accident, the timing of this type of thing. So we already had, in some sense, the input deck that we could use at least to get a first-order analysis of what was going on at Fukushima. The other thing is a large U.S. presence in Japan. There's an Air Force base not too far from the Fukushima site. There's many U.S. personnel. And so this really amplified the need for the U.S. government to engage actively in this. So I think it was on the day after the accident that there was a kind of working relationship forged between the NRC, DOE, INPO, and the Department of Defense on how to work together through this. So NRC activated their emergency operations center. People were deployed to Japan from NRC to help support the embassy and the government of Japan in understanding how to cope with the accident. The ambassador to Japan was looking for information. He wanted to be able to advise U.S. citizens in Japan about what they needed to do. And we set up these coordinated consortium calls that involved NRC, INPO, DOE, and naval reactors. So INPO's role was really to help organize the industrial response to assist TMI. So many of our companies wanted to send over pumps or tanks or various equipment to help with the accident. And the government, in some sense, couldn't pick and choose who to get, so we let INPO do the clearinghouse of that, put together the capabilities, and work directly with TEPCO and the government of Japan to provide the information so that there would be some ability for industry partners to cooperate or to support the efforts there. Unfortunately, a lot of the protocols that were not in place that were probably needed to do this seamlessly, and so I would say that the industrial support was slow. In DOE, we activated the Emergency Response Center, and we're interested in monitoring the impact on U.S. citizens, both in Japan and the U.S. NNSA deployed their airborne monitoring system, aircraft and sensors. We provided people to the embassy as well. We sent several national laboratory representatives to provide technical support. And within DOE, we stood up what was called the Science Council, which was meant to advise the Secretary of Energy on actions on a day-to-day basis. And the Department of Defense got involved in providing equipment and capabilities to assist Japan. So it was quite a strong interagency effort to provide U.S. response and support. In terms of, and again, what we were trying to principally interested in is really, what was the radioactivity that was released? What is the consequences going to be on people? And then so we termed this source term estimates. The DOE response to the accident used following capabilities. We were getting timely information on plant parameters, meteorological forecast, radiation measurements, so we could use that. And then that was coupled in with our phenomenological modeling, including the use of the code MELCOR and then NARAC. And these were then used to help inform the government officials in the U.S. about what was the likely distribution of the radioactivity both in Japan and about the transport of radioactivity to the west coast of the United States. In terms of aerial monitoring, NNSA very rapidly deployed their aerial monitoring equipment. This was both fixed wing and helicopter overs, be able to map out the radiation deposits out to 80 kilometers from Fukushima Daiichi. And then this provided data to support decisions on evacuation, relocation, and agricultural decisions. They also supported the establishment of ground monitoring, both mobile and in situ, doing air sampling, contamination swipes, just a wide variety of monitoring, including radioactive isotopic mix. And we're again using this data then in coordination with the analytic work to really do the assessment of the potential consequences that then informed evacuation and cleanup activities. Just to give an example of some of the accident collection that was going on, we were able to get data fairly early on in terms of things such as water level, pressure in the reactor vessel, these type of things. We had information about the venting that was occurring, reflood, and what was happening in terms of the various parts of the system. And we had some data, and we're using that to understand trends and cross-checks, and could use that then to recommend additional data sampling. We obtained data from many, many sources, and I will say that it was quite a job to keep up with things. So the Japanese Atomic Industrial Forum had reports. The FEPC did. We were watching the Japanese television, NHK, and they were reporting, information from the site. So we were trying to capture that information as well. We had our aerial photographs that we were trying to use to understand the extent of the damage, and then later, in particular, what was going on in the spent fuel pools. We had thermal imaging, reports from Japanese government, and from TEPCO. So it was quite a wide range of information exchange, and we were in constant contact with our Japanese colleagues via phone calls to try to convey to both us and to them what we thought was going on and what the next steps might need to be. This just gives an overview of sort of all the analysis that we were doing within the first couple weeks of the accident. From a DOE perspective, we were interested in long-term effects of the accident. You know, could the reactors be stabilized? Would there be, if another earthquake happened, you know, some other kind of major release? The NRC was more worried about the day-to-day operation, how to keep the core cooled. We were looking out months in the future and trying to make extrapolations about what may happen, because there were a lot of things that were new territory to us. You know, the one thing that we quickly came to the conclusion of, that because the ultimate heat sink to the reactors had been lost, you just are going to have to wait a long period of time before they would come into a cold shutdown state. And as we ran the numbers, it ended up being something on the order of 300 days. And that ended up being pretty close to the time it took. So as people thought that this was going to be over quickly, I think we were quickly able to inform them that this was going to be a long-term thing in terms of just getting it stable. And then based on our TMI experience, the cleanup is going to be decades long. So this was kind of important information that we were able to get very quickly after the accident. Now at the time, you know, we were all still had significant uncertainties. And after the explosion in Unit 4, there was a great concern that the spent fuel pool had gone dry and there might be a fire of the zirconium releasing even more radioactivity. So the NRC chairman at the time, you know, testified that to this effect to the House and Energy Committee, and this then led to you know, emergency evacuation zone that was probably larger than it needed to be. But again, it was based on this erroneous conclusion that the hydrogen explosion in the Unit 4 came from hydrogen from the spent fuel pool. We now know that the hydrogen came from Unit 3 that was through one of the vent systems, and that the spent fuel pools were okay. But this was a great area of concern about a week after the accident. And so we spun up the laboratories to begin looking at a variety of things, and in particular looking at the thermal analysis of the pool. So we had some information very early on, in large part because we had sent people immediately to Japan, and they were able to understand what the spent fuel in this pool was, what the decay heat levels were, so that they could put together rather rapidly a modeling of the pool and try to calculate how long it would take to boil down. And what we found was that it could take a considerable period of time, much longer than when the explosion actually occurred. So, you know, from this analysis, we were starting to think that there was, in fact, still water in the pool, and that the zirconium fire had not occurred in the spent fuel pool. I should also add that we also we're looking at the gamma shine from at the pool as the aerial monitoring system went over. And if there was water in the pool, you would expect a quite different signature than if it was dry. And we used a Monte Carlo analysis to basically conclude that there had to be some shielding because the shine was too low if the pool had been dry. So then again, some other evidence that there was water in the pool. As I mentioned maybe before, but because of the work we had done at Peach Bottom, we used our Melcor code to do a lot of analysis early on. This code has data from various sources from around the world in it. I'm not going to go into the details of the modeling, but it models the melt progression, fission product release, these type of phenomena in the vessel, but it also does the tracking and the containment. And because of this, we can actually then get ultimately how much, you know, what's the magnitude of the source term, the fission products released to the environment. You know, one way to get at this is to compare the code to the available data, and if you can get the water level about right and pressure as a function of time, then you're probably close to getting, you know, the actual response. And if you do that, what you find out is that, you know, for the Unit 2, that of the volatile fission products, nearly 95% of them were released from the fuel, but most was retained in the suppression pool. And then eventually, if you go to the environmental release, it was somewhere on the order of 1 to 3%. You know, seemingly a small fraction, but actually quite important, because that's about the range of the cesium released to the environment, which is still something to be very concerned about. At the same time, we had our best estimate modeling capabilities put into play, the NARAC. This does much more detailed modeling of the plume, bringing in worldwide data, this type of thing. This was looking at a plume that was generated and whether it would transverse the Pacific Ocean and what would we expect to see on the west coast of the U.S. It was also looking at, given the various weather patterns, what the direction of the radioactive dispersal would have been around the plant. And then this was augmented with Raskell and Melchior modeling and gave us at least some idea of what the protective actions would need to be for the hypothetical scenarios that we were using. So this was used to inform the emergency planning. And of course, there's lessons learned reports, and we're still, I think, learning from that. And I was mentioning to some of the folks beforehand that in a couple of weeks there'll be a meeting at the NRC at the Regulatory Information Conference where we'll talk a little bit about some of the efforts in the U.S. and Japan to begin to think about what you would need to do as you decommission the plants in terms of collecting data that could be useful in further improving our understanding of severe accident phenomena. So some thoughts for the future. With new designs being built, it will be important to have the international community share analysis results. So in the past, there's been some of that, but I think that needs to be intensified through either Nuclear Energy Agency or the IAEA. And I think we need to stay cognizant of accident scenarios in non-U.S. origin design. So in some sense, because we had extensively studied the General Electric design, we were in fairly good shape to be able to respond to the questions from our leadership in government. But if it's a Korean design or a Russian design, Chinese design, I think we would be in a not such a good position. And so I think we need to be looking at how do we in some meaningful way get to the point of having at least some level of cognizance about the accident scenarios in these non-U.S. origin designs. So in summary, this issue of source term estimation is very complex, a highly technical issue. We need to be as realistic as possible. Again, being overly conservative is probably not helpful. But to get that realistic, you need a suite of analysis capability, data collection capabilities, and accuracy and credible data are very important to this realistic estimation. And I think then the other point I've tried to make is that the capabilities, resources need to be ready and available and need to be periodically exercised for optimal performance. So this gets to emergency preparedness, various capabilities there, but I think also the types of risk studies that have been done by the NRC in the past at least put us in a position of understanding what could happen and then allowed us to more quickly be able to use that information to guide the decision-making process. So with that, thank you for your attention and be glad to answer any questions.
I'll pass the microphone around so our online listeners can follow along. Please introduce yourself before you ask a question.
There we go.
Okay, sorry for the delay. Hi, my name's Jeff Glick. I'm adjunct prof here at Virginia Tech, teaching emergency management type courses, and also work at DHS. Question today, I did a stint at OSTP as a detail Office of Science and Technology Policy in the White House, and Dr. Holdren, the individual I worked for, was advising the president in Fukushima. The same time, I guess you were advising Dr. Chu at DOE. And there's a lot, as you mentioned, there's a lot of different sources of information for models, et cetera. Did you two coordinate your communications such that the information going forward to the White House was coordinated between DOE and, say, OSTP?
Well, Dr. Holdren participated in the meetings we had with the secretary. So he was one of the people that were there. We were doing twice-a-day briefings. Dr. Holdren was there, or he had a surrogate, and was either there in person or was on the phone. There were other Nobel laureates that were on the panel, so they were asking the tough questions, and then we were having the laboratories go out and run the analysis to try to answer the questions that were coming from the Science Council. So yes, it was very, very well coordinated.
It's really a follow-up to that question. John Medeiros, adjunct professor here at Virginia Tech. In a former life, I was an airborne damage assessment, nuclear fallout prediction person for the Air Force. Command and control is hugely important, and you talked about this variety of agencies, and yet the international picture. Was there any single activity that you would say was coordinating all of that to help things on the ground in Japan go as smoothly as they could go?
Well, certainly through the National Security Council, there were frequent phone calls that brought in all the different players to make reports. So there was a kind of a constant stream of that. We I think probably both NRC and DOE we had our emergency response centers stood up. We were gathering data. We're making daily reports to the White House. So I think there was a strong effort there. I know the Deputy Secretary actually had a strong role in trying to achieve that coordination. So, but I think it really was coming from the White House, both OSTP or the National Security Council, that was kind of leading the charge and making sure that we were all keeping ourselves informed.
Questions, comments? You're next, Kevin.
I'm Doug Chapin. John and I know each other. We've been together a lot of time. I've worked at Fukushima post-accident and been on several committees and the like. I think the big message there was they had never thought about having an accident, and they never prepared for it. So it wasn't a matter of they didn't have the analysis tools or that sort of thing. It was, they never assumed they had an accident. They never practiced in the plant doing that. They never got the government lined up as to how they were going to get people done. All of that, was not in the cards. And that was one of the things we learned after 3 Mile Island, is we hadn't done that, and so we said we're going to work on that in the future. I think the Ukrainians and the Russians had the same experience. So I guess I'm looking for your thoughts on this. I would think one of the big lessons out of all these big severe accidents is you better sit at each plant and say, I think I had one of these, and figure out what it is I'm going to do, and then get everybody to practice. And I don't mean sit down and have a practice. I mean, really work at it and do this over and over again. Do you have that same sort of reaction?
Yeah, I think that was one of the strong lessons from TMI was this establishing much stronger emergency response actions, including evacuation and having those type of things understood in more details. You're right. The Japanese hadn't thought this was possible. Somehow they were able to evacuate people rather rapidly. I think the Fukushima accident was the slowest evolving of the three. TMI was about 20 minutes or an hour maybe. Chernobyl was almost instantaneous. You had about a day in the Fukushima case. So I think that having that time allowed the people to understand what's going on, evacuation to be ordered, and they followed. They did evacuate. But I think that's the important lesson from protecting the people, at least in the initial throes of the accident. But I think there's these longer term consequences which you really you don't know what the long-range issues might be, and so if you can make some projections of that, you can be better prepared for what you need to do in the future.
I would agree with that. I just make it
Yeah.
that in the evacuation in Japan, there were a number of people killed. It wasn't people who died from radiation. It was because they hadn't thought about how they were going to do the evacuation.
Yep.
How they were going to get the people out of the site and what they were going to do with it.
Yeah.
So a lot of the people that talk about were lost after Fukushima had to do with the recovery and the lack of preparation and thought as to how one was going to deal with that if you had a real accident.
Right.
Thanks for your talk. My name is Kenneth Wong. I'm with the graduate school in the physics department here at Virginia Tech. You talked about the importance of having kind of accurate and timely information. I wonder, especially given the way news travels now, have you done work on how to stop disinformation from spreading in the aftermath of an accident like this?
Yeah. Well, I think in particular in the Fukushima case, we had several experts that had a pretty good idea of what was going on. And so when someone or some entity made an assertion about a particular topic, that we took it upon ourselves to disprove it. And looking at it from the different angles, whether it's the radiation level, the water level, etc. And so we wanted to convince ourselves that it was probably not the case. It just didn't make sense. But we had to look at it from a variety of angles. So having that group of experts available that can quickly, come to a counter hypothesis, basically, and then put together the evidence to show that it probably didn't happen. This was the bulk of our activity during that first month or so after the accident.
Dan Blumenthal, Department of Energy. On your summary slide, your bullets about needing realistic estimations and needing exercise capabilities. So taking and source term estimation, taking those things together and looking at Chernobyl and Fukushima were very long-lasting releases, and in the United States, when people try and exercise response capabilities, they always exercise very short duration, simple releases, which don't reflect the two large accidents we've seen in history. Can you comment on, what scenarios we choose to exercise, and if there's any suggestions on ways to do things differently?
Well, I have not been myself involved in the exercises, so I don't know the nature. I know a lot of the concern had been over dirty bombs and things like this, and being viewed to maybe be more probable than large.
Just on reactor accidents.
Yeah, just on reactor accidents. Well, it's hard to. It's hard to know what actually is going to happen. So you have to sort of be ready for kind of a spectrum. I think the analysis that we've done shows sort of a limited range of radioactive material dispersal. Okay, I mean, this has been largely helps inform then the size of the emergency preparedness zone. And so if you've got that kind of there and that, then you can focus on that emergency preparedness zone and figure out how fast do you need to evacuate people, what are the roadways, and these things can be practiced in advance. Now, you may have very long-term cleanup and consequences, but if the people are evacuated, then at least the human health effects will be very limited. You'll still have, I think, expensive and costly cleanup, but you've basically significantly reduced the threat to humans.
I just wanted to encourage our online participants, if you have a question or a comment for Dr. Kelly, to email it to siren@vt, as in virginiatech.edu. We have one online question from Frank Kitchig, a nuclear exercise specialist from Canada, who asks if you could say a few words about improving emergency response readiness. And if I may tag on to that, how would DOE capabilities better or different from those that already exist at NRC, that INPO manages? And also, another question that I had about the summary points that you showed us: how would you translate this technical information into what can be actually implemented as a policy, whether it's to evacuate or to organize some kind of response?
Well, let's see. So, in the U.S., a lot of our expertise resides in DOE laboratories. So, both NRC and DOE have access to that expertise. NRC has also developed their own analytic capabilities and have worked closely with the utilities in the U.S. to develop what's called accident management guidelines. And there's sort of a set of procedures that take you through step by step on what you should do. So, in my view, when we were tackling the accident and its consequences, NRC was devoting their resources to day-to-day kind of what needs to be done next, how much water, how do they hook up fire hoses and things like this, right? DOE was looking more long-term. They put a lot of salt water into the vessel. So would that mean that in 6 months the vessel would corrode and everything would fall out of it? These were questions that we could then turn over to our specialists at like Oak Ridge, who would then look at corrosion rates and things like this and come up with a determination that it could be a threat, we need to worry about it, or it's so long-term that we don't need to worry about it. And then because people were saying salt water is going to destroy everything, and so we had to come up with a technical basis for concluding otherwise. So we were looking at longer term, how many days before cold shutdown could be removed or achieved without ultimate heat sink, and a variety of other questions like that. So I think in the end, the technical capabilities were kind of in the same place for both NRC and DOE, but they were being exercised for different reasons. And then you had a follow-on
how you translate the technical material, the technical information you gather into what can be actually used in policymaking.
Well, I think the way we did it was that we had the Secretary of Energy established the Science Council that was there to advise him, but they would be asking kind of the questions, and it's through that question and then the analysis activity that we were able to take what's fairly detailed and distill that down into something that was much easier, because the people on the Science Council weren't necessarily severe accident experts. They were just highly technical, and many of them communicators and had been informed policies in the past, and so it was through that kind of consensus body that we were able to get the technical information and then put it into a form that could be used by the policymakers. And so I think in the end, it was more to try to calm down the rhetoric and try to understand actually what was going on and not have it become sensationalized and create panic and fear. And so this is what I think having these kinds of capabilities in place allowed us to do that rather rapidly.
Okay, thank you. Any other questions? Comments? Well, I have lots more, so I'll just keep going. How did you mentioned this accident data collection that happened almost instantaneously after Fukushima started. How were issues of Japanese sovereignty negotiated while collecting data?
Well, I think Japan was publishing the data, and so we were making sure that we captured it because we knew we would, continue to have a need for it, and if it may not be, it needed to be captured and archived. It took us a while, but eventually we worked through and have an intergovernmental agreement for information sharing. There was some hesitancy, initially on TEPCO's part to share the information because of concerns about the proprietary nature of the data, and we had to work through that. So it took a while before we could get this intergovernmental agreement in place, but we had other agreements in place that we were able to exercise and eventually get that. But in the early days, the data was being published. There was information on the TV that I was recording on DVD the NHK and then playing it back in the morning because we're 12 hours different, and being able then to get their science report. And they had, I think, I was really kind of surprised that the news coverage seemed to be, really trying to provide good factual information, so it was that kind of an activity.
So you relied mostly on published data? Yeah,
but as I said before, there was various sources. TEPCO, METI, MEX, JAIF, they were all sending information. I think what we had hoped at that time was that the IAEA would have had a stronger role in data collection and sharing, but they too had not really, they too weren't really prepared. And what that means is that they didn't have the staff to man an emergency operations center, where that's basically the way you put people together and you give them the job of collecting data as it becomes available. Subsequent to that, the IAEA has launched a program where they asked for their staff to volunteer for this emergency response training, and they have a couple hundred or maybe more hundred of their staff have that training now. So if there is an incident anywhere in the world, they can bring people into their emergency response center, man it, and begin to do that kind of job of collecting data and providing it to the world.
Just a quick question. Did the DOE, I'm Jason Donovan, I'm not with anyone. Did the DOE use SI units, or were they using traditional US units?
We were using SI, and it was, we had never really thought about sieverts versus REM. Just like if you read this newspaper article from TMI, there was confusion about units at that point too, about REM per hour versus REM and things like this. And it was, it's a pretty easy translation, but it was not that we didn't know what the, how to communicate that, and so the public didn't understand REM, very much less sieverts. So it was, we're kind of fighting an uphill battle there on that one. But at least we were trying to talk in the SI units.
Adi Haigat, professor and director of nuclear engineering at Virginia Tech. I just want to follow up on the question you just got. Why not set a standard on units? Because this is really, even for me, when I hear million micro or million milli, or it takes me a few minutes or second at least to convert. Yeah. And we expect the regular people somehow understand these things and absorb it. And so why not, as a community, which I'm part of it actually, to set a unit just like Fahrenheit, centigrade. We have units.
Well, I really don't know why the U.S. hasn't adopted SI. I mean, I have some view that maybe there's a commercial reason for it. That we have to do a lot of retooling or something like that. But it's sort of, you got to go all or nothing. Because in the end, you have to sort of internalize the unit. So, you know what 80 degrees Fahrenheit means, right? But in some sense, it's just a number, right? But if you had been brought up understanding sieverts or millisieverts, and you said you got 1 millisievert, you would know what that in terms of health effects, because you would be able to correlate that to, how much radiation you get in an airplane and that type of thing. There was some suggestion that we go to the banana. The banana measure, like 2 bananas gives you equivalent of this much radiation, and so we just would talk in terms of bananas that people could relate to. But I think there's some truth to that, but it's sort of going to the opposite extreme. Yes.
Yeah, there was a good National Academy of Science workshop on going to the SI unit about a year ago, and They haven't come out with. They might have come out with the proceedings by now, but there were lots of pros and cons. I think on the industry side and the retooling you mentioned was one of the major stumbling blocks.
We could have a unit for the public. Internally, you can use whatever unit you want. You see what I'm saying? I really think that very fact that we cannot properly communicate what is the radiation level. Yeah. It's really causes significant damage to information that we communicate with the public. I mean, public really, even C-word or whatever you tell them, they really don't understand it.
Right.
So because they are not trained on the subject, and it's not like temperature, you feel it, unfortunately, in a certain way. But I truly think as a community, we really need to think about this and do it, irrespective of some company wants to do whatever, because with the communication with government and people, we could have a unit.
So let me just mention something that is an initiative that American Nuclear Society with NEI and others have launched. It's a K through 12 educational initiative where we're going to put together, working with the Discovery Network, a package on nuclear science and engineering, nuclear science and technology, that we would basically push out to first to the middle school and then high school, elementary, which could maybe get at this so that we start early in the education path of students and hopefully get them some better understanding of what radiation is, what its effect is, so that when they're in their adult days, they will actually have this understanding or have that kind of background. Right now, there's the education on this topic is very limited in elementary, high school, and so I think this initiative that ANS is pushing right now, I think, is needed for the long term to try to get at this problem you're talking about.
My name is Armin Masale. I do work with the International Red Cross Federation, both on Fukushima and Chernobyl. I think, in essence, there's two issues. One is that the science and the politics of this, the science being trying to determine what the exposure is, what the risk is, et cetera. The politics politics are the decision to make evacuation, inform the public, et cetera. And there are other examples of this. If use tornado watches, hurricane watches, those type of things. The public really is not into knowing the details of millibars and storm directions, et cetera. They just know when the Hurricane Center issues a warning and the political decision is made, they evacuate. So I think that there's, in each one of those examples, even 3 Mile Island, Chernobyl, and then Fukushima, there was that issue of trying to translate quickly that the public could understand what is the risk, what they should do, and to do it on a timely basis. The second thing is, and I know in particular in Fukushima, and to a certain degree in Chernobyl, you had the scientific authorities doing things, and then you had the talking heads, and trying to issue the official line, whereas on the news channels, et cetera, they always had someone that could give, and sometimes contradictory information, which caused confusion. Even in Fukushima, where Americans were told it had to evacuate within 70 kilometers, 50 miles of the event, and the Japanese were telling their people 10, 15 miles, et cetera. So again, it's that reconciliation of the science of this is the risk, this is what we should be telling people for protective actions, and then being cognizant of what the political ramifications are of that.
Yeah. Yeah, you're correct. When you have a tornado warning, we know that because of empirical data on atmospheric conditions and what that could potentially lead to. So, this happens frequently enough that people understand that it's, this is what we should do in that type of a situation. If you're worried about radiation and radioactive contamination, health effects, this is a very complicated problem. It's not, and so all you can do is really try to exercise your capabilities and try to understand what the reasonable range of consequences might be, so that if you do have the accident, you can give your best shot at informing the public. But it is not, in any sense, a simple thing to do.
Just to follow up on that question, I think the issue is also trust, right? Trust in information. And if you have contradictory information like the one that was published after Fukushima, how far to evacuate. And by the way, you showed us a few plume images.
Yeah.
People were not evacuated according to the scientific predictions of where the plume would go. They were evacuated in concentric circles from the plant. So how is a rational member of the general public who may not be familiar with millisieverts or whatever the unit is you're using supposed to trust public officials if they tell them to evacuate in a straight radius around the plant, when the scientific information points to a different kind of area that might become affected?
Well, I think the actual path for the radioactive contamination was very much dependent on the wind direction, which can, in some sense, be all 360. And so, on some days, the wind was blowing out into the ocean, and at that one particular point in time, it was going up into the north and the west. So, I think evacuating in a concentric way makes sense to sort of guard against the possibility that should be subject to the wind direction on a particular day. So I think there's some merit to doing that. But I think what through risk studies and things like this, you can gain some information about what's the distance that the consequences could be had, and then you need to use that to basically inform your emergency planning zone. So it's those two things in place, and then if you have that, then you have capabilities in place to do the evacuation and help people in the case of the accident. But you can't just. There were some studies done in the early 80s that were using superbounding kind of source terms. These led to a lot of fear on their own. So you really need to try to use best estimate. But again, do all the sensitivities so that you have an idea of what possible consequences might be there. But it is limited. It's not unlimited. It's just a matter of trying to understand what that limit is and then do something about that in terms of your emergency preparedness zone.
We have one more question from Frank Kitching here. How often are nuclear emergency response exercises conducted with the participation of the state and national government organizations with a role in nuclear emergency response? In your opinion, is this essential for preparedness?
I actually don't know that. Maybe one of my NSA colleagues.
I think in the United States, relicensure requires an exercise every 2 years that's conducted by FEMA for at least a domestic nuclear power plant. So they exercise at least once every 2 years in the States. I don't know what it is in other places.
Sorry, I can add to that, and I am not speaking on behalf of the Nuclear Regulatory Commission, but I'm speaking on the basis of just finishing 12 years there as their spokesman. The headquarters at the NRC runs 4 full-fledged drills every year in conjunction with the various plant drills that are conducted. And some of those drills are related to fuel cycle facilities as well. So they run the gamut.
Yeah, so I haven't participated in any of those, so I don't, but I'm glad we have some members of the audience here that have some information on that.
All right. Any other questions, comments? Well, please join me in thanking John Kelly for a great conversation on the great talk. Thank you.
Thank you. Is that okay?
Yeah.